Focus. Focus on something. Focus. There you go, dude. Alright, just has to be stroked a little bit. Nice fun. Alright, anything else from homework stuff? Yes? Whatever you want to talk about. Q2? 33. Oh, okay. All right. So that's one thing we're going to kind of practice on today. This is 2 number 33. Minus x over x squared. Yeah, cool. I like it. All right. Is this an indeterminate form? Careful. So what's indeterminate form mean?
Oh, no, it's not. It has to be 0 over 0.
Yeah, it's either 0 over 0 or infinity over infinity. Well, we haven't seen that yet really too much, but and there's some more beyond that, but that's going to come up later. So if it's one of those, that sucks a little bit. It means you have to do some work before you can determine the answer. That's why I love that name. It's indeterminate at the moment. Is this indeterminate?
No, it's undefined.
All right. It's undefined at that point, but the limit, you have to be more specific about what the limit is. Don't just say does not exist. Well, it's technically true. Bless you. Bless you. Right. If I said, is this a dog or a cat? And you say it's a mammal. Okay, technically you're right. But be more specific. So, okay. Is everybody with me? What form is this in? When you plug a 1 in, what form does it take? 1 over 0, right? Which is called undefined. It's also called something else sometimes. Anybody else's teacher call it something else? Infinite. I like it. Because what's 1 divided by really, really small? Really, really big. I like it. Okay, let me stop here for a second. So as x goes to 1, the bottom is getting stupid small. So the whole thing is getting stupid big. So now the question is it positive infinity, negative infinity, or not agreeing? You see how, am I going from one side or the other? Am I approaching 1 from the left or the right, or how am I approaching 1? Is there a little plus or minus up here? No. So I'm coming at it from both directions, so they have to agree. Okay. So what does this mean? I'm curious about what happens when x is really close to 1. So when x is really close to 1, what's the top always? Positive or negative? When x is really close to 1. Positive. Don't say, well, at 3 it's negative. Well, that's 3 is not really close to 1. Right. When I say really close to 1, I mean 1.001, 1.00000. Stop. You guys still with me? So I know this is undefined, which really is better called infinite in the context of limits. Because it's going to go to infinity or negative infinity or, not agree. Now I just got to determine which one of those is it. Is the answer infinity? Is the answer negative infinity? Or is the answer does not exist? Because then they wouldn't agree if they do this, right? Like my shirt. Okay. So the top is positive. The bottom is positive, negative. It's always freaking positive. We're not using complex numbers, thank God. So when I square a real number, I always get positive, unless it's 0. And it can't be 0 because it only happens at 1. Yeah, shit. So the whole thing is always positive near 1. Therefore, the limit is positive infinity. I love it. You might even want to put a little plus sign, just to really make sure that there's no stray mark that makes you think it's negative. It's positive. So this, if you graph this in your calculator, you'll see it do like this at 1. That's why the answer is infinity, because these agree. It doesn't exist. There is no ceiling, but it doesn't exist in a specific way. They agree that it goes to positive infinity. If it was this, they would agree it goes to negative infinity. And of course, this, they don't agree, so it doesn't exist. How do we feel about that? So, when it's not indeterminate, that means you can get the answer. But if it's undefined, that's some kind of infinity. So what would it have been if it would have been this? Why negative infinity? Because the top for x is near 1. The top would be negative. I love it. That's all it takes. I know it's some kind of infinity because the bottom 0, the top 8. Just to show off my grammar. So now I just got to figure out what kind of infinity, or is it just purely doesn't exist because it kind of depends on which side you come from, right? So this one, they agree on both sides. This would be negative infinity because it's negative everywhere close to 1. If you graph this one, it'll look like that at 1. I like it. So it won't look like this. All right, cool. Is that decent? We're going to do some problems like that for practice later. So we'll do some more of those. Anything else from homework stuff? Okay, no. All right. So, oh shit. Better fix the fan. And I turned it on, that's awesome. Okay, so what I want to do is, I kind of want to, we got to do a few things in Sue 3. And then I got to skip 2.4 for a minute. I'm going to go to 2.5, and then we'll come back and do 2.4. 2.4 is that proof section. We sort of already talked about 2.5 a little bit, so that's why I want to kind of get in there. It connects really nicely, and then we'll do 2.4. Let's do 2.3. Start off with something just to make sure you guys all understand something about this. What would that be? So no tricks. What is it? 4. Yeah, I love it. The limit as x goes to 2 of x squared is 4. Now we're going to kind of overlap a lot. There's something interesting about a parabola, or this type of function. Is it, can I connect it just by one stroke of the pen? Do I have to pick my pen up to make this graph? No. So that's the idea of continuity. So we're going to talk about continuity in a bit, but the limit as x goes to 2 of this is equal to the function value there, because it's continuous. It gets to where it looks like it's going to. It's a nice function. It doesn't have this jump thing, doesn't have a big pothole in it, right? So it gets to where it looks like it's going to. So to figure out the limit, I actually just have to figure out what it is at 2. It's going to equal that, because there's nothing weird about this function. So I can just plug a 2 in and get the answer. Now, this is kind of silly. The section is a little bit silly. Let me see if you guys can catch it. What's this? So we go 3. So 4 minus 8, negative 4 plus 7. That's right. So you're playing along at least. Right. All right. So when the function is nice, which we're going to define more specifically to be continuous, that means that every point in the domain of that function, not only does it look like it's going to it, it actually gets there. That's really what continuous means. So to evaluate nice functions, I just got to throw the damn thing in there. Now, I want you to remember, what's the thing we just did earlier? Did we throw it in there to see what form it was in? And then we can go from there. So that's where we always start. We throw it in. Is it something I can't figure it out? Do something. Factor it, conjugate, multiplication, right? Or if it's something I can figure out, do it. If it's a nice function, you're done. It's just plugging shit in. Notice something that you guys just thankfully just take on faith. The limit of the difference in sum of things is the difference in sum of the limits. If I plug a 2 in there, I get 4. If I plug a 2 in there, I get -8. So I can just combine each individual limit. That sort of is like, well, of course, Jeff. Hopefully you guys are like, I didn't even stop to think about that. I just put a 2 in, man. That's beautiful. That's what this whole section 2.3 is about. Guess what? You can put shit in and add them. It's amazing. All right, so there are these limit laws. One of them says this. The limit as x goes to a of f of x plus g of x equals the limit as x goes to a of f of x plus the limit as x goes to a of g of x. Oh my gosh. So the limit of the sum is the sum of the limits. Cool? Okay. And the difference of the limit of the difference is the difference of the limits. And remarkably enough, the limit of a, what about this? What do you guys think about this here? What's the limit as x goes to a of a constant times a function? What can I do with that constant?
Constant terms.
A little bit weird. But like, what's the limit as x goes to 2 of x? 2. What's the limit as x goes to 2 of 3x? It's 3 times the limit as x goes to 2 of x. It's 3 times 2. It's 6. So I can take that out if I wanted. Some of these are so basic you don't even really think about them as you do a problem. Here we had a -4 coefficient. We didn't stop to think, oh, am I allowed to? No, we just did it, which is fine. Okay. It's when we have undefined functions and we're trying to do a proof, that's where these kind of things really come in handy. Okay, I like it. What do you think about the limit of the product of two functions? So basically I can do this. Hopefully you guys are cool. So that's a minus, that would be a minus. If that's a times, that would be a times. If that's a divided by, that would be a divided by as long as this limit is not 0. Okay? So things that just make sense. So this is divided by. This is divided by. If this limit is not 0. These are all listed out in a table in section 2.3, so you can keep notes if you want to, but they're all right there for you. All right, how are we feeling so far? I mean, we've already used these laws before, without realizing we're using these laws. Oh, let me jump to the chase here. Oh yeah. Okay, ready, look. Where are you, little theorem? You're coming up. Look. There's stuff that we're going to come back to later. For example, how do you think I can rewrite this here? This is a little bit. So for example, if you did a specific problem, like the limit as x goes to 3 of the square root of x squared plus 1, what would you do? Plug a 3 in. So officially, this is the square root of the limit as x goes to a of f of x. Right, you bring the limit inside. We don't even think of it that way. We think of it as plug a 3 in the damn thing. There's an important idea behind this. When we talk about continuity, as long as the function is continuous, you're allowed to bring the limit inside of it. So if there's a function that's nice, that is continuous. Oh, my grammar's horrible in this question. If f of x is continuous, there you go, then the limit, yeah. Got it. You can bring the limit inside. All right, not too bad. So this little section is kind of just making sure you know what things look like more abstractly. So when we do some proof stuff, we have to be able to use these directly, these limit laws. But we already do them, so I just want to point out that we do them already. Oh, we already know that. Oh, here's a freaky theorem. So the list of all the limit laws are in there. You can take a look if you want to. So there's limit laws. Once we get to continuity, a lot of those limit laws just become one statement, which is the statement I just put down here. If it's continuous, you're allowed to bring it in. All right. Here's the last thing in this section 2.3. Something you're not going to believe I didn't name myself. What is it? It's called a squeeze theorem. So the idea is really kind of nice. It's if I want to investigate a function I'm not really sure of, this is one way to do it. So if f of x less than or equal to g of x less than or equal to h of x. So basically this says for all x in the domain of those functions. So that's true. So basically g's output is always in between f's and h's output. So one example picture would be, here's g. There's g. Here's f. Let A be the place where they're equal to each other. And, well, it's supposed to be less than Jeff. That's good job. We'll call this an H. This one will be F. It's very important to get this idea right there. So G is always in between F and H. F is like the floor. H is the ceiling. F for floor, H for high. I don't know, somewhere. So what is the limit? Let me say this is, call this L. What's the limit as x goes to A of h of x? L. And what's the limit as x goes to A of f of x? L. Let me stop here for a second. But let's say g of x itself is a funky thing. But I know that g of x is always in between these two functions. You see why it's called a squeeze theorem. So if h is easy, I can tell what the limit is easy. And f is easy, I can tell what the limit is easy. And g is freaky as all shit, but I know it's always between those two. What must the limit as x goes to A of g of x be? L. It's the only thing it could possibly be. It's squeezed. It's always got to be between the two. And if those two both go to L, I always think about the end of the Terminator, the 80s one, the first one, when the turn gets pushed. If the top and the bottom of that press meet, then the Terminator is terminated. Yeah, he's dead. So this thing squeezes it in. The only thing that could possibly be then is L. That's beautiful. That's why we call it the squeeze theorem. That's crazy. So let's do an example. Let me see. Let me get a kind of a I like it. Yeah, this is a pretty one. I like it. All right, now help me out. Now watch. This is how this almost always works. What piece of this is bounded? See, this whole thing is the idea of being bounded. What piece of this is bounded? You know what I mean by bounded? It can only go up so far, down so far. What piece? Say again? Square root of x goes to infinity.
Each of them.
Yeah, cosine x is bounded. But don't think about 0. If I say a specific number, then everything's bounded. It's, but that generally is bounded. It can't go be above 1. It can't go below -1. So what is e to the cosine x in between? Always. Yeah, it's greater than or equal to e to the -1 and less than or equal to e to the 1, because cosine is in between -1 and 1. Okay, I like it. Now, believe it or not, I mean, this is the first step. What we're doing is we're constructing the function they're asking me about, using things I know. That is awesome. I know this is true. That piece of it is there. I know this is true. What's missing to make the middle equal the function I'm curious about? What's missing? What's the middle missing that my function has? Square root of x. So if I multiply by square root of x, now take the limit as x goes to 0 of everything. Since this is always in between these, this limit has got to be in between these. And what's the limit as x goes to 0 of a constant times square root of x? 0. Because when you plug a 0 in, it's 0. And what about this? 0 for the exact same reason. Who gives a shit about e? E is tiny compared to infinity. 0 times not infinity is freaking 0, right? So therefore, what must be true about the limit as x goes to 0 of this function? It's got to be 0. There, that's the squeeze theorem. You find what part of the question is bounded. You write that by itself. Then you multiply in whatever else is missing. Then you do limits, and these should agree. That's the whole idea. If they ask you to use a squeeze theorem, they better agree, because that's supposed to squeeze it to be that value. Maybe. Actually, it's almost too nice to believe, if you think about it. That's a really simple little dude. Hopefully. I know that you guys are not used to building functions. You're not used to taking a part of the question and then building from there. But that's completely legal. Because I did get what they're asking me about eventually. I just set up a way for me to do it now. This whole idea of constructing what we want is going to come back when we get to 2.4, that little proof section. All right. Any questions on that? That's probably the freakiest part of 2.3 is that squeeze theorem. The rest of it is those limit laws that are pretty straightforward. Okay. Help me out here. What would you do here? What you got, Jeff? Put a little from above there, just to make it all legal. And of course, the mistake people would make is they start doing conjugate business. Why is that completely unnecessary? Is this indeterminate? No, it isn't. Right? What do you get on the top when you plug a 2 in? 5. And what do you get on the bottom when you put a 2 in? 2. Okay, so that's it. So my point there is, I am going to, and so is the homework, you're going to sprinkle in problems where you don't have any extra work to do. You just plug the number in, you're done. So don't start factoring, multiplying by conjugates, just because you're like, oh, I'm doing something. No. Make sure you got to do anything. Is it indeterminate? That's the only time you have extra shit to do. Right? If it's not indeterminate, that means you can determine the answer. So determine the answer. Done. I like it. Because you get so wrapped up in all the different methods to simplify inside of limits that you just start throwing them everywhere. It's like, no, you didn't have to do it there. Don't do that. Okay. So let's talk about continuity. And then I've got a little worksheet for you guys to work on. And then we'll do this 2-4 proof stuff. Now, let me just give you a graph. Let me ask you, where is this thing continuous? So my question to you is, where, let me say it like this, where is f of x discontinuous? And I know we haven't even defined what that is fully yet, and I don't seem to care. Oh, Jeff. Well, I'm not grading you on this shit. I just want to see if your gut kind of tells you. Now, there's some obvious places where this is discontinuous, and we're going to give them names. Yeah. So the first place this is discontinuous is at 1. What does the function do? It looks like it's going here, and then it jumps. Look at me leading you. So this is called a jump discontinuity. Isn't that awesome? That's so much better than, it's a Schwartz discontinuity because it's Schwartz. No, screw it. It's a jumping, right? So this at x equals 1, there is a jump discontinuity. Okay. Where else is there discontinuity? At 2. And what kind of discontinuity would you call that? Why is it discontinuous? Because the function goes to
Infinity.
Ah, good. So it's an infinite discontinuity. Yay. Right. So at x equals 2, there is an infinite. Infinite discontinuity. But infinite dis. It's infinitely dis at 2. What about at 3? I made that a point, but what's up with 3? Is that discontinuous there?
No.
Why not? Try to be very specific. What do these two don't have that this has going for? This is not discontinuous because why was this discontinuous? Because the limits on both sides don't agree. So here, the limits on both sides agree. So the limit as x goes to 3 from below equals the limit as x goes to 3 from above. But I could very easily do this, and that would be discontinuous, right? This one is kind of neat. This one would be called a removable discontinuity. If there's a hole somewhere, you can remove it by just filling that hole in. Right? So this one would be called a removable discontinuity. So if you want to put a little note, this is removable. Jeff, not Romeo. Removable. The removableness. Isn't that an awesome word? Yes.
So how did it like now it's not included?
Beautiful. So let me put this back. Right? In your notes, you might want to draw yourself a little example. This is a removable discontinuity. If there's a pothole, I can remove the pothole, right? Which sounds a little bit paradoxical. You take the hole. I can remove it by filling it in. I could define this to be this value at 3, and then the discontinuity is gone. I can put a bridge there, right? Here, no. There's no way to remove that discontinuity, right? And if you're like, let me put a bridge this way, then it's not a function anymore. It doesn't pass the vertical line test. Oh shit. Okay, maybe. All right, now, so like I said, that's not enough. That could be this. So what is it that makes it continuous is that not only do those limits agree, but they equal the function value there. They equal the function at 3. Think about it. Not only does it look like it's going somewhere and they both agree, but it actually gets there. That's continuous. Let that make sense. Please. It's not horrendous. Some of you guys look like you just ate old snails or something. I'm sorry. Okay. Unless you like old snails. I don't like fresh snails. Okay. So here's the definition. Let me give you a formal definition of continuity. One, the limit as x goes to a of f of x from below equals L, which is the limit as x goes to a from above. 2, L equals the function evaluated at a. So not only do they agree on a limit, but that limit is the function value at a. So I think there's 3 things in the book because it says they exist or whatever, but that's basically what this is saying. The quick way to say this, you can say this in one fell swoop like I did over there. Limit as x goes to a of f of x equals f of a. That's the quick way to say it. The limit from above and below agree, and they agree on the function value at that point. That's the quick way to say what continuous is. Amen. I think I've given you. Given you enough. This is nifty. The first problem on this is a problem like we just did with the graph. Second one's a nifty one. I'm going to do problems like the second one. I'm going to ask you to create a graph that meets certain requirements. It's always exciting. Third one is a piecewise function, which a lot of you seem to not enjoy at all. So piecewise functions aren't that important. Yes?
Do you have to create a function when you create the graph?
No. Well, thank God. Yeah, it would be really hard to figure out a function that does everything I want it to do. All right, let me just give this to you. You can work together if you want, or you can work alone if you really want to be a wolf pack alone. Just put the side with 2-5. Don't worry about the side with 2-4 yet. They have some nifty Greek letters that we don't know what they mean yet.